Our goal is to review correlation from a statistical point of view, then we jump into Python. So what is correlation? Correlation is basically finding a relationship or association between variables. Suppose a safety inspector wants to determine if there is a relationship, association between, for example, two variables. One of those variables can be the number of hours of training for an employee, and the other variable can be the number of accidents involving that employee. So how do we find a relation? Do we find a relation by just looking at the data, or we have some numerical way to evaluate that relation? Suppose a psychologist wants to know if a relationship exists between two variables. For example, this is just an example. One variable can be the number of hours a person sleeps each night and that person's reaction time. Or what is a relationship between the number of minutes a student or a person check their TikToks and the frequency of their online purchasing? So these are the types of questions that you're going to answer. These are correlations. How would you determine if there exists any relationship between two variables? To answer this question, we're going to study correlation. Describe what type of relationship in any kind exists between two variables. Basically, when we're talking about correlation, we're talking about quantitative variables, numerical variables, and how to determine if the correlation is significant. Let's go over basic definition from a statistical point of view, then we do the coding. A correlation is a relationship between two variables. The data can be represented by the ordered pair x comma y as we used in algebra to help visualize dots and points in xy plane. In statistics, in data science, in machine learning, we call x independent or explanatory variable, and y is called the dependent or response variable. So if you open different data science, machine learning books, you might see independent or explanatory, and for dependent variable, you might see response. So how do we visualize the points? The graph of ordered pairs like x and y is called scatter plot. In a scatter plot, the ordered pairs like x and y are graphed as points in a coordinate plane. The independent or explanatory variable x is measured on the horizontal axis, and the dependent or response variable that we denote by y is measured on the vertical axis. When it comes to stock market, we use time series analysis. For time series analysis, on the horizontal line, you have t time. On the vertical line, you have the stock price. That's a different story. Here we are basically just working with simple relation between variables. A scatter plot can be used to determine if a linear or straight line correlation exists between two variables. The scatter plots below show several types of relation between two variables. For example, you might have a negative linear correlation. So as x increases, the value for y start decreasing. And we can fit a line passing through these points. And as you can see from left to right, the line is decreasing. In this case, we say that we have a negative linear correlation? Well, you might have a positive linear correlation as well. The trend between X and Y shows that you have an increasing line. As X increases, Y tends to increase as well. And we can fit an increasing line from left to right with positive slope down here. And for a negative linear correlation, slope of the line is negative. Well, sometimes we can't find any correlation in this case. Like if you have IQ score and the height, you have many variables that are not correlated. We basically can't find a recognizable pattern here. So we say that, hey, there is no correlation. You might see non-linear correlation as well. So in this case, we have a parabola, right? We also talked about stock market. For stocks, we have a trigonometric representation, sine and cosine. So we have different types of correlation. Not all of them are necessary linear correlation. Sometimes we have nonlinear correlation as well, which has a different story, which is not in the context of this class. So how do we construct a scatter plot? In order to construct a scatter plot, you just need to plot the dots in XY plane. Let's go over one example together. An economist wants to determine if there is a linear relation exists between a country's gross domestic product, GDP, and the carbon dioxide CO2 emissions. Well, that person collected some data. Let us visualize the data and then plot these in XY plane and try to see if we can get some meaningful information out of them. So the GDP in trillions of dollars, which is denoted by X, independent variable or explanatory variable. You have 1.7, 1.2 trillions of dollars, 2.5 trillions of dollars, and so on. So you have a bunch of X values. They also calculated the CO2 emissions for those countries. So for example, if the GDP of that country is 1.7 trillions of dollars, its CO2 emission is 552.6 millions of metric tons. If the GDP is 1.2 trillions of dollars, the CO2 emissions is 462.3 millions of metric tons, and so on. So please note that the data is not written in order. You have 1.7, then you have 1.2, then it jumps to 2.5, and so on. The minimum value is 0.8, and the CO2 emission associated to that value is 253 millions of metric tons. So let us try to visualize this. We have our X values that we're going to locate on X-axis, and for the vertical line, we're going to use CO2 emissions. Very good. So our very first dot is going to be 0.8, 253. This is basically coming from algebra, plotting these dots in XY plane. From the smallest value, so it just jumps up, goes down, goes up, down, up, and up. So there are some noise in the data that we see here, but still we can recognize a linear pattern. So this is from visualization point of view. We can see a linear pattern, increasing trend. It seems like as X increases, Y increases as well. So as the GDP increases, we expect to see an increase in CO2 emissions. But we need mathematical formula to verify this. So from the scatter plot, it appears that there is a positive linear correlation between these two variables. Our interpretation is that reading from left to right, as the gross domestic products increase, the carbon dioxide emission tend to increase as well. So here we see a linear correlation between the data. How strong that linear correlation is, well, that depends on the correlation coefficient. Let's take a look at another example. A student conducts a study to determine whether there is a linear relationship between the number of hours a student exercises each week and the student's grade point average GPA exists or not. So the data are shown in the table below, displaying the data in a scatter plot and describe the type of correlation. Our X value is independent. It changes freely, which is the hours of exercise. 12 hours, 3 hours, 0, 6, 10, 2, and so on. So what is the GPA of the student who exercises for 12 hours? That GPA is 3.6. If a student exercises for 3 hours, their GPA is 4. No exercise, GPA is 3.9. 6 hours of exercise, 2.5, and so on. So you have X and Y. Our goal is to visualize this and see if we can find a recognizable pattern here. The scatter plot shows on the left, and we see that with 0 hours of exercise, we have GPA of 3.9, which is located here. The next point is going down, then up, down, stand still almost, go up, go down, go up. So we don't see any recognizable pattern. So for now, with these data, we don't see a recognizable pattern. So if we collect more data, if we add more values to our table, we might be able to see a recognizable pattern or nothing at all. But again, we still need a mathematical value, a number that basically help us to make sure we have a correct analysis of the data. What is correlation coefficient? Interpreting correlation using just a scatter plot or visualizing the data can be subjective. A more precise way to measure the type and the strength of a linear correlation between two variables is to calculate the correlation coefficient. Although a formula for the sample correlation coefficient is given, it's more convenient to use technology. So let us basically define the correlation coefficient and see what is the formula behind this when we are doing the coding and using this function. What is the behavior? What values you're entering into your formula? How do we change that? Later on, if you try to optimize an algorithm and you're working with correlation coefficient related topic, you need to know what is this formula. The correlation coefficient is a measure of both strength and the direction of a linear relationship between two variables. For a sample correlation coefficient, we're going to use R. R represents the sample correlation coefficient. Formula for R is basically N times the summation of X times Y minus the summation of X times the summation of Y divided by the square root of N times the summation of X squared minus the summation of X to the second power, and you have the second square root, N times the summation of Y squared minus the summation of Y's to the second power. N is the number of pairs of data. And again, please note that here we are using R as the sample correlation coefficient. When it comes to population, the correlation coefficient is denoted by Greek letter rho. So this is your population correlation coefficient. In the book and some of the code exercises, they ask you to basically write a function calculating the correlation coefficient. But using NumPy, you can basically call that function and calculate the correlation coefficient. So each library has different functionality. Decide which function, which library you want to use, so you know which function belongs to which library. The range of the correlation coefficient is -1 to 1 inclusive. It means that it can be -1 or it can be 1. When x and y have a strong positive linear correlation, r is close to 1. When x and y have a strong negative linear correlation, r is close to -1. When x and y have perfect positive linear correlation or perfect negative linear correlation, r is equal to 1 or -1 respectively. When there is no linear correlation, r is close to 0. It's important to remember that when r is close to 0, it doesn't mean that there is no relation between x and y. It just shows that there is no linear relation between x and y. You might be able to find a nonlinear relation. Several examples are shown below. For example, when the dots are lined up perfectly and it shows an increase, it means that you have a perfect positive correlation. R is equal to 100% or 1. For example, the number of adult movie tickets, and on the vertical line, you have variable total cost. They have a perfect positive correlation. Well, sometimes the data are a little bit scattered. You have some noise, but still you can recognize a pattern. It means that in that case, you have a strong correlation. If that pattern shows an increasing line, it means that you have a strong positive correlation. For example, like 81%. You might be able to recognize the pattern, but with more noise. In that case, you have a weak correlation. If you can fit a line, increasing line, then you have a weak positive correlation. For example, in that case, you're going to get a correlation coefficient which is close to 50%, 45%, and so on. The same for negative correlation. If the dots are lined up perfectly and you see a decreasing trend, it means that you have a perfect negative correlation, or R is equal to -1. If there are some noise, but still you can recognize the pattern easily, it means that you have a strong, in that case, negative correlation because the line is decreasing. For example, the correlation coefficient that is associated with this graph is -0.92. And finally, if you have some noises, but still you can recognize the pattern, and instead of going up, it goes down, you have a weak negative correlation. And sometimes there is no linear correlation at all, like IQ score and the height. Maybe we can find a nonlinear correlation between them, but not a linear one. So what are the guidelines here? In the interview, if they ask you to write down a code for the formula for correlation coefficient, you need to know the step. First, find the sum of x values, the summation of x. Then find the sum of all y values, the summation of y's. Multiply each x by its corresponding y value and find the sum, the summation of x times y. Step 4, you're going to square each x value and find the sum, the summation of x squared. Number 5, square each y value and find the sum, the summation of y squared. Use these 5 sums to calculate the correlation coefficient that we talked about in previous slide. Basically, it is n times the summation of x times y minus the summation of x times the summation of y divided by the multiplication of 2 square roots. Square root of n times sigma x squared minus sigma x to power 2 times the square root of n times sigma y squared minus sigma y to power 2. For example, let us go back to our GDP and CO2 emission example. How do we calculate the correlation coefficient? Does this number help us to find a correlation between these two variables? Remember that our scatter plot shows that we should have a positive linear correlation or positive linear relation between these two variables. Let us calculate R value. Remember, first you multiply each x and y. This is the multiplication of x and y. You're going to repeat this for each line. And then you're going to square x values. 1.7 times 1.7 gives you 2.89. Then you square each y value. 552.6 multiplied by 552.6. And then what you're going to do, you're going to repeat the process for each pair of x and y's. X times y, then x squared, then y squared, and repeat the same process. In the final step, you're going to add all x values, add all y values, add all x times y's, add all x squareds, and finally add all y squared. Because in the formula, we're going to use each one of these. With these sums and the fact that n is equal to 10, you have 10 pair of values. The correlation coefficient formula is as follows. So let us plug in everything here. N is equal to 10. We know that. The summation of x times y, we calculate that guy here. Then the summation of x, which is 24.6, multiplied by the summation of y, which is 52.63. Now do the division. Your first square root is n, which is again 10, multiplied by the summation of x squared, which is 79.68, minus the summation of x, which is 24.6 to power 2. You're going to repeat the same thing for your y values. If you do the calculation, R is very close to 0.912 or 91.20%. What does it mean? Remember that if you get a number which is close to 1, it means that you have a strong positive correlation between these two variables. What is the interpretation? It means that as the gross domestic product increases, the carbon dioxide emissions tend to increase as well. So in order to make predictions, remember that we collected data. Regression equations are often useful for predicting the value of one variable, given some specific value of the other variable. When making predictions, we basically should consider the following cases. First of all, you might have a bad model. If the regression equation doesn't appear to be useful, for making predictions, don't use the regression equation for making predictions. Simply, you need to move on to other mathematical model. For bad models, the best predicted value of a variable is simply its sample mean. But the sample mean is not a good predicted value because it is the predicted value for any value of the other variable. 2. For good models, we're going to use the regression line for predictions only if the graph of the regression line on the scatter plot confirms that the regression line basically fits the points reasonably well. Number 3, correlation itself. Use the regression equation for predictions only if the linear correlation coefficient, or R, indicates that there is a linear correlation between the two variables. And number 4, if we are looking at the scope, use the regression line for predictions only if the data do not go much beyond the scope of the variable sample data. Remember that predicting too far beyond the scope of the available sample data is called extrapolation, and it could result in bad predictions. So we can't just go far away from the data that we have because we have the danger of extrapolation, bad extrapolation. Perfect. So now let us introduce regression line. After verifying that the linear correlation between two variables is significant, the next step is to determine the equation of the line that best fit the model. This line is called regression line. Its equation can be used to predict the value of y for a given value of x. Although many lines can be drawn through a set of points, a regression line is determined by specific criteria. It basically needs to minimize the summation of residuals squared. Consider the scatter plot and the line shown below. For each data point, like these points, you have 1, 2, 3, 4, 5. You have a difference between the actual y value and the predicted y value. These are called residuals. So the actual y value or the observed y value and the predicted y value. The predicted y value is located on this line. If the observed values are below the line, you have a negative residual. If your observed y value is above the line, then it means that you have a positive residual. When you're building and constructing a regression line, for that regression line, it must minimize the summation of residual squared. This is what machine learning do. So as we mentioned before, these differences are called the residuals and can be positive, negative, or zero. When the point is above the line, the difference between larger y value and smaller y value is positive. And when they are below the line, the difference between the smaller value and the larger value is negative. When they are exactly located on the line, it means that the difference between the actual y value and predicted y value is zero. But remember that our goal is to find a regression line or a line that makes the summation of residual squared to be minimized. This is an important criteria. Okay, we defined the regression line in using the residuals and just the visualization. But what about the mathematical model behind it? A regression line, also called the line of best fit, is the line with the sum of the squares of the residuals is minimum. Remember that in algebra, you just need 2 points to graph a line. If I have these 2 points here, then I can easily find the slope of the line and the y-intercept and use y equals mx plus b to write down equation of the line. In algebra, you learn that you can write an equation of a line by finding the slope between 2 points and the y-intercept. The formula was basically y equals to mx plus b. But in data science, we don't have just 2 lines. We have many points. So in algebra, we have 2 points, we get 1 line out of it. But in data science and statistics, we have many points and we can graph many lines. But which one is the regression line? It must satisfy the criteria that the summation of residual squared is minimal. So again, to find the y-intercept, when you have y equals to 2x plus 1, you set x equal to 0 and you get 1 as the y-intercept. But how do we find y-intercept when it comes to statistics and data science? That is the question that we try to answer. The equation of a regression line for an independent variable x and a dependent variable y is denoted by y hat equals to mx plus b. So y hat is the predicted y value. It's not the actual y value. So y hat is the predicted y value for a given x value. We can calculate slope and the y-intercept of the regression line this way. So as you can see, we are going to take into account all of x and y's and use them to calculate m, or the slope of the line. This is n times the summation of x, y's minus the summation of x times the summation of y's divided by n times summation of x squared minus the summation of x to the power 2. And in order to find the y-intercept, it is y bar minus mx bar. Y bar is basically the average of y values. M is the slope that you calculated here, and x bar is the summation of all x values. So by using the average of x and y's, you can find the y-intercept. And then write the equation of regression line. So as we mentioned, y bar is the average of all y values, and x bar is the average of all x values. And n is the number of pairs of data in your collection. The regression line always passes through the point x bar and y bar. So let's go back to our previous example. We want to find the equation of regression line for gross domestic products and CO2 emission. How do we do that? We need to find the slope of the line, and also we need to find the y-intercept. But we have a nice formula. And again, in Python, we have functionality that can calculate these values easily for us. M, or the slope, follows the formula n times summation of x, y's minus summation of x times summation of y's that we calculated in previous example. So we don't have to recalculate these. We just punch this into the formula and we see that, hey, slope of the line is 166.9, which is a positive slope. Now, for your y-intercept has a nice formula. Y-intercept is y bar minus m x bar. But we calculated m just right here. We need to find the average of y values, find the average of x values, and punch them here. So it seems like our b, or the y-intercept, is close to 116 or 115.73. Remember the visualization of the scatter plot. If we just basically graph this line, y hat equals to 166.9 times x. Don't forget x, guys. This is a line. Plus 115.725. This is the regression line. Hopefully, this is the line of best fit. And as you can see, it passes through x bar and y bar. Remember, we had a good correlation coefficient, and we could find the equation of regression line. Now, I expect you to ask, what about the variation about regression line? How do we analyze those? What is the relationship between x and y and those variation? How much of a variation can be explained using x, and how much of the variation cannot be explained using x? So in this section, you're going to study two measures used in correlation and regression studies: the coefficient of determination and the standard error of estimate. You'll also learn how to construct a prediction interval for y using a regression equation and a given value of x. So the topic that we're going to discuss later, building confidence interval and hypothesis testing. Before studying these concepts, you need to understand the three types of variation about a regression line. To find the total variation, the explained variation, and also unexplained variation about a regression line, first you need to calculate the total deviation. Okay. After we define total deviation, we can talk about explained deviation and unexplained deviation for each ordered pair, like x sub I and y sub I. These deviations are shown in the figure. So for total deviation, you have the difference between the actual y value and the average y. This is total deviation. So you have the actual y minus the average y. Explained deviation is defined as the predicted y minus the average y. You also have unexplained deviation, which is basically each y value minus the predicted y value. You can visualize them as well. So for example, suppose you have basically a point. This is your point, xi, yi. This is your regression line. Of course, you can see a difference between the actual y value and the predicted y value. This is called unexplained deviation. You also have a difference between the predicted y value and the average y's, which is defined as explained deviation. You also have a difference between the actual y value and the average y value, which is called the total deviation. So now that we define total deviation, explained deviation, unexplained deviation, we are ready to talk about total variation, explained variation, and unexplained variation, and how to interpret that in the context of statistics and data science. The total variation about a regression line is the sum of the squares of the differences between the y value of each ordered pair and the mean of y. So we can write it this way. Total variation is the summation of the difference between the actual y value and the average y and raise it to the second power. The explained variation is the sum of the squares of the differences between each predicted y value and the mean of y. Or you can write it this way. Explained variation is the summation of the predicted y value. Remember that when you have y with a hat on top of it, this is basically the predicted y value minus the average. You're going to raise it to the second power. Otherwise, if you add them all together, you might get a 0. For unexplained variation, this is the summation of squares of the differences between the y value of each ordered pair and each corresponding predicted y value. We can write it this way. Unexplained variation is the summation of the difference between the actual y value and predicted y value to the second power. And as we mentioned before, the sum of explained variation and unexplained variation gives you the total variation. In summary, total variation is the summation of explained variation and unexplained variation. So how do we use these definitions? We're going to introduce the coefficient of determination. The coefficient of determination that is denoted by r squared is the ratio of the explained variation to the total variation. We can formulate that this way. The coefficient of determination, or r squared, is the division between explained variation and total variation. It's important that you interpret the coefficient of determination correctly. For instance, if the correlation coefficient is 90%, then the coefficient of determination is 90% multiplied by 90%, or just 90% to the second power, which gives you something a little bit different. It is 81%. What's the meaning of that? It means that 81% of the variation in your y can be explained by the relationship between x and y. The remaining 19% of this variation is unexplained, and it's due to other factors. Like what? Like sampling error, coincidence, or lurking variables. What is the standard error of estimate, or S sub E? The standard error of estimate is the standard deviation of the observed y values about the predicted y hat value for a given x value. We can define it this way. The standard error of estimate is defined as the square root of the summation of yi minus yi hat to the second power divided by n minus 2. N is the number of pairs of data. So in order to define the standard error of estimate, or S sub E, we need the following. First, make a table that includes the 5 column, including xi, yi, the predicted y value, and the difference between the actual y value and the predicted y value, and make sure to raise it to the second power, because inside the radical, after you're raising these to second power, you're allowed to add them together. to use the regression equation to calculate the regression line, which is y hat equals to mx plus b. Calculate the sum of the squares and then divide them by n minus 2 and then take the square root. So again, all of these can be found using in a good library, the standard error of estimate. This is the math behind this. So for example, let us go back to our GDP and CO2 emission example and are interested in calculating the standard error of estimate between X and Y. Remember, we calculated the regression equation. Y hat was equal to 166.9x plus 115.725. Our goal is to find the standard error of estimate. Step by step, we can calculate that. We're going to use a table to calculate the sum of the squared differences of each observed y value and the corresponding predicted y value. Xi's, yi's, we need to plug in each x value to find the predicted y value and then find the difference between these two values and square them. So yi minus yi hat, the difference between the actual y value and the predicted y value, and then we're going to raise them to the second power. So you have yi minus yi hat to the second, and these are the values. Now you're going to add them all together, the whole values in this column, and finally divide them by n minus 2. And then finally take the square root. Our standard error of estimate is about 116.492. So this model appears reasonably strong due to high coefficient of determination, but here you have a high standard error, all right? Suggesting that while the model captures the general trend well, individual predictions may still vary significantly. So you might need to change to a different algorithm or a different model and evaluate the error again and compare these two errors. If we want more accuracy in individual predictions, we might consider adding other variables or refining the model as well. Let us move on to predictions. Data science is often used to make predictions about the future. If we are trying to predict an outcome for a particular individual, for example, how a person responds to a treatment, or if they buy a product or not, it's natural to base the prediction on the outcomes of other similar individuals. The table below is adapted from a historical data set on the heights of parents and their adult children. Each row corresponds to one adult child. The variables are a numerical code for the family, the heights of father and mother, the number of children, as well as child's birth rank. 1 represents the oldest, being male or female, and basically the height. Let me type the code in the chat for you, so you can replicate this in your Jupyter notebook. Make sure to import important libraries that you're going to use. Define a function to generate the scatter plot for you. And make sure to read the CSV file. So if you read the table, you have some variables, and some of them, for example, are binary. 0, 1s, representing male and female. And what is important is the child's height, based on the height of the father and mother. A primary reason for collecting the data was to be able to predict the adult height of a child born to parents similar to those in the dataset. So we're going to try to do this by using the simple average of parents' height as the variable on which to base our prediction. This parent average height is our predictor variable. In the cell below, its values are in the array parent underscore averages. If you look at the table heights, it consists of just the parent average heights and child heights. The scatter plot of two variables shows a positive association, as we would expect for these variables. So let us take a look at our Jupyter Notebook codes. Calculate the parent average. And visualize the table with only 2 columns. And then generate a scatter plot. So now you have just 2 columns. So the parent average height is 72.75 and the child height is 73.2. The parent average is 72.75 and the child's height is 69.2. Okay, some of them are close, some of them are just a little bit off. So can we say that, hey, the average parent height basically help us to predict the child's height? This is the question that we want to answer. The breakdown of the code is, for example, for this line, it calculates the average height of parents for each family. Then, as you remember, table creates a new empty table for you, and this table basically is part of the data science library. For those of you who don't feel comfortable working with data science library, absolutely fine. Feel free to use the regular Python libraries. With columns, this method is used to add columns to the newly created table. And finally, the parent average is the name of the first column being added to the table. This column will represent the average height of the parents. And the parent underscore averages is the data for this column. It contains the average height for each family, calculated earlier, by finding the average of the height between father and mother. So the question is, what is the relationship between a child's height and the average parent's height? This is the question that you're interested in answering. Let us make a scatter plot. Our very first step, as we saw in statistics, is try to visualize. A scatter plot helps us to visualize x and y's in xy plane. It can help us to detect any relationship between variables. In this case, our variables are parent average and the child height. So please run the code in your Jupyter notebook to be able to visualize the scatter plot. On the horizontal line, you have the parent average, and on the vertical line, you have the child height. Okay, even though we see noises here and there, we can still recognize a linear pattern. You basically say, hey, we can fit a line here. And it seems like we have a positive trend. Suppose the researchers encountered a new couple similar to those in the data set and wondered how tall their child would be. What would be a good way for him to go about predicting the child height, given that the parent average height was, say, 68 inches? What's the mathematical formula that we're going to use here? One reasonable approach would be to base the prediction on all the points that correspond to parent average height of around 68. So we're looking at nearby points. The prediction equals the average child's height calculated from those points alone. Let us execute this plan. For now, we just make a reasonable definition of what around 68, close to 68, in the neighborhood of 68 means, and work with that. Later in the course, we'll examine the consequences of such choices. Okay, we're going to take close to mean within half an inch. So for now, just take this as the close by points or neighboring points in the same neighborhood. The figure below shows all the points corresponding to a parent average height between 67.5 inches and 68.5 inches. These are basically all the points in the strip between the red lines. Each of these points corresponds to one child, which is our prediction of the height of the new couple's child, which is the average height of all children in the strip. That's represented by a gold dot. So please run the line of code. Should be on your Jupyter notebook or your Google Colab. So by running this line of code, what do we see? We have two vertical lines capturing all the points that are close by to the gold point here. So this is almost the idea behind when you're, for example, having a new movie and you want to have some classification for that movie. Is this a horror movie? Is this, for example, thriller movie? What kind of movie is that? You're going to use other movies that are already there with their genre and with their specification, and you're going to find the neighboring points. So this is the basic idea behind it. But this is simply explained through the height of parents and children's. So this is the breakdown of the code for you. The heights.scatter. This creates a scatter plot with data from the height table. The parent average column is plotted on the x-axis, as you can see, as you can visualize. And on the vertical axis, you have the child's height. Some more specification for the plot and what's the meaning of 67.5. This line basically adds a vertical line to the plot, x equals to 67. So if you just look at this point, this is 67.5. And then for the y coordinate, these are basically between 50 and 85. We set the line width to be 2, which makes the line thicker than the default. More explanation for the second line. So what is our conclusion? Well, in order to calculate exactly where the goal dot should be, we first need to identify all the points that are close to that value. This corresponds to the rows where parent average is between 67.5 inches and 68.5 inches. So we're going to define close by in the neighborhood, close to 68. We're looking at the heights where the parent average are between 67.5 and 68.5. It generates the following for us: the parent average and the child. Okay, 68, 74, 68, 70, 68, 68, 68, 67, and so on. The predicted height of a child who has a parent average height of 68 inches is the average height of the children in these rows. That's basically 67.62 inches. So if you look at the average gives you 67.62. We're using NumPy. We now have a way to predict the height of a child given any value of the parent average height near those in our data set. We can define a function, predict_child. Let me type it in the chat for you so you can run this in your Jupyter notebook. So the body of function consists of the code in the 2 cells that we described in previous slides, apart from choices of names. So we basically define a function, predict_child. We're going to pass in p average. So this function predicts the height of a child whose parents have a parent average height of p average. The prediction is the average height of the children whose parent average height is in the range p average plus or minus that nearby value, which we agree to be 0.5 inches. These are close by points. All the heights where the parent average are between the p average minus close by points are defined like this: p average minus 0.5 inches and p-average plus 0.5 inches. So the heights that were basically filter the heights table to select only the row where the parent average is in between the ones that we are interested in having. But again, for now, just take 0.5 inches plus minus to define close by points. Given a parent average height of 68 inches, the function predict underscore child returns the same prediction, 67.62 inches, as we got earlier. Remember that. You're interested in using a function. Why is that? Because you can pass in any value and it just calculates that y value for you easily. For example, if I pass in other values, like what? Like 68. This is my input value. This is my function that I defined up here. And the output value is calculated super fast at 67.62 for me. You can pass in another value. Like, let us predict the child. The p-value, p-average is 66. In that case, we expect the child height to be 66.08, 64, and so on. We're basically finding the predicted y value, or as you remember, y hat that we described at the beginning of the class. But the question is, do we have good predictions by using just the average height of the parents? Is that a good prediction? Or do we need to calculate the residuals as we discussed before, minimize the summation of residual squared to get the best regression line? We can get a sense of this by comparing the predictions with the data that we already have. To do this, we first apply the function predict underscore child to the column of parent average heights and collect the results in a new column and we label it prediction. Okay, let me type this in the chat for you. So you run the code. So let us create a new column. This is our table, the parent average, the child's height, and the prediction. Okay. The parent average is 72.75. We're just looking at some of these values. The child height is 73.2, and the prediction is 70.1. Okay, there are differences here. Then you have 72.75, 69.2, and the prediction is 70.1. Remember, our goal is to find the best mathematical model that makes the best predictions for us. To see where the predictions lie relative to the observed data, we can draw overlaid scatter plots with parent average as the common horizontal axis. Please run the line of code. Okay, here we have our visualization, right? Here we have these dots. The behavior is similar to an increasing line, right? But how do we get the formula for this line? The graph of gold dots is called a graph of averages because each gold dot is the center of a vertical strip like the one that we drew earlier. Here we created a graph of averages, but is this the best predictor? Help us to make a prediction, or we need something else? This is our very first attempt to making predictions about children's height. Remember that. Each one provides a prediction of a child's height given that parent average height is there. We have those pieces of information. We're going to use them. For example, the scatter plot shows that for a parent average height of 65 inches, the predicted height of the child would be just above 65 inches. And indeed, predict underscore child 65 evaluates about 65.84. Notice that the graph of averages roughly follows a straight line. This straight line is now called the regression line or line of best fit, and is one of the most common methods of making predictions. The calculations that we have just done is very similar to the calculation that led to the development of the regression method using the same data. Let the fun begin. Correlation. Correlation from Python point of view. In this section, we're going to develop a mathematical measure of how tightly clustered a scatter diagram is about a straight line. We already saw the formula. We know the behavior of the formula. Formally, this is called measuring linear association. Now we're going to move on to a different CSV file, which is called hybrid. It contains data on hybrid passenger cars sold in the United States from 1997 to 2013. The data were adapted from the online data archive of Professor Larry Wiener of the University of Florida. The columns are vehicle, which is the model of the car, year of manufacture, MSRP, or manufacturer's suggested retail price in 2013, acceleration rate in kilometer per hour per second, MPG, or fuel economy in miles per gallon, and the class, which is the models class. Let's take a look at our data. Let me type the code in the chat for you. Please make sure to change the directory. Your file is stored in a different directory than mine. In more complicated versions of the data, for example, you might be interested in analyzing customer churn. For example, the customers who subscribe with AT&T or any different provider. What are the reasons that they stick to the plan? And what are the reasons that they just go on to a new plan with a new service? So customer churn is also an important and interesting machine learning models that you might have heard about. We're going to talk about customer churn when we delve into more machine learning algorithms. For now, let's just work on a single regression line. Here, let's take a look at the data for hybrid cars. As we mentioned before, we have some columns, some variables, vehicle, year, MSRP, acceleration, MPG, and the class. So we have good data. We are interested in making some predictions. The graph below is a scatter plot of MSRP versus acceleration. That means MSRP is plotted on the vertical axis and acceleration is on horizontal. You can switch these two. You can make connection using X and Y using different order. Later on, we're going to create a heat map, and basically you're going to see the correlation coefficient for each two variables. So let us take a look at the acceleration and MSRP. And as we mentioned, acceleration is going to be on the horizontal line and MSRP is on the vertical line. So the retail price on the vertical line and the acceleration is your free independent variable, and the price depends on the acceleration. Well, even though we have a lot of noises here, we still can recognize a pattern. Notice the positive association. The scatter of points is sloping upward, indicating that cars with greater acceleration tended to cost more on average. Conversely, the cars that cost more tended to have greater acceleration on average. So you can read X to Y or Y to X. And as we mentioned, we see an increasing trend. But the question is, having a linear trend like this, does it mean that we have a good correlation coefficient? Do we have a good mathematical measure describing the relation between X and Y? The scatter diagram of MSRP versus mileage shows a negative association. Hybrid cars with higher mileage tends to cost less on average. This seems surprising till you consider the cars that accelerate fast tend to be less fuel efficient and have lower mileage. As the previous scatter plot showed, these were also the cars that tended to cost more. So let's take a look at our MSRP and MPG. Let me share the code with you so you can run them in your Jupyter notebook. Along with the negative association, the scatter diagram of price versus efficiency shows a nonlinear relation between the two variables. The points appear to be clustered around a curve, not a straight line. So this is the behavior that we see. So this is not a linear relation. This is curved, non-linear. If you restrict the data just to SUV class, the association between price and efficiency is still negative, but the relation appears to be more linear. The relation between the price and acceleration of SUVs also shows a linear trend, but this is a positive slope. So let's just take a look at the class of SUVs and take a look at the scatter plot of MPG and MSRP. Basically, what we see here is different from what we had before. Now we are just restricting ourselves to a specific class of SUVs. So even though we have a lot of noise, but still we can recognize a linear pattern. Now for the SUV class, if we take a look at the scatter plot of acceleration and NSRP, we see, even though we have noises here, we see an increasing trend. Now let us define the standard units or the z-scores. It basically converts any array of numbers to standard units. As you remember, for a z-score, you're going to take the x value, the actual value, minus the mean, divided by the standard deviation to have a z value or a standardized value. The function standard underscore units is used to convert any array of numbers into a standard unit or z-score. You basically take the number minus np.mean, you basically calculate the average, and after finding the difference, you divide it by the standard deviation. This is what we learned in elementary statistics at the beginning chapters. For any numbers or list of numbers, this is basically an array you want to convert to standard units or z-scores. We can use this function to redraw the two scatter diagrams for SUVs with all the variables measured in standard units. So now on the horizontal line, you're going to see different scale. So if you look at the table with columns, all in standard units, MPG and MSRP, basically the visualization, the behavior of the scatter plot is the same as before, but the units, the scale on the horizontal line and also on the vertical line are centered at 0, and 1 unit to the left, 1 unit to the right, 2 units to the left, 2 units to the right, 3 units to the left, 3 units to the right, and the same here. So now we can visualize all of these in a standard scale. You're basically creating a new table with columns, MPG and MSRP in standard units. The following code creates a scatter plot to examine the relationship between acceleration and MSRP of SUVs in standard units. The same behavior as we saw before. We see an increasing trend, but again, the units on the horizontal and vertical lines are more scaled. And here is the breakdown of the code. As usual, table with columns, restrict them to the columns that you're interested in using. And then you're using a scatter plot, and you set the limit for the axis as well. Now, the question is, how can I visualize all of these scatter plots for all of these variables in one page? You're going to use Seaborn. Take a look at the code, run it in your Jupyter notebook. It takes a few seconds, and it generates all of these scatter plots for you in one page. So you don't even have to create the scatter plot for two variables separately. This way, you can basically visualize all of scatter plots in one page using Seaborn. make sure to convert your table to a data frame and SNS.pairPlot and just pass in your data frame. Basically takes each two variables and generate a scatter plot showing relation between two variables. For example, here you have MSRP and MPG, which we saw its nonlinear relation. For example, here you have MSRP and acceleration. Here you have acceleration and MSRP. As we saw, it's almost an increasing trend, and so on. Very good. So far, we visualize the scatter plot. We visualize the relationship between x and y's. What is our correlation coefficient then? Remember the formula for correlation coefficient. N times the summation of x, y's minus the summation of x times the summation of y's divided by the square root of these two quantities. Remember that the correlation coefficient measures the strength of the linear relationship between two variables. Graphically, it measures how clustered the scatter diagram is around a straight line. The term correlation coefficient isn't easy to say, so it's usually shortened for correlation and denoted by R. But again, remember that for a sample, you're going to use R. For population, we're going to use rho. Here are some mathematical facts about R. The correlation coefficient R is a number between -1 and 1 inclusive. It can be 1 or -1 as well. As we discussed before, the correlation coefficient R measures the extent to which the scatter plot clusters around a straight line. R is equal to 1 if the scatter diagram is a perfect straight line sloping upwards, and R is equal to -1 if the scatter diagram is a perfect straight line sloping downwards. The function R underscore scatter takes the value of R as its argument and simulates a scatter plot with a correlation very close to R. Remember that because of randomness in the simulation, the correlation is not expected to be exact. So again, in your Canvas assignments, when you're solving problems and you get a number a little bit different from the value that you see, absolutely fine. We are using simulation. If you call R underscore scatter a few times with different values of R as the argument, we can see how the scatter plot changes. When R is equal to 100% or 1, the scatter plot is perfectly linear and slopes upward. When R is -1, the scatter plot is perfectly linear and slopes downward. And as you remember, where R is equal to 0, the scatter plot is a formless cloud around the horizontal axis, and the variables are said to be uncorrelated. It means that they are not linearly correlated. They might have other type of correlation, like nonlinear correlation. And as a quick review, we talked about the range of correlation coefficient between -1 to 1 inclusive. And as long as they are close to 1 or -1, we have a strong linear correlation. Otherwise, we have a weak linear correlation, and when they are equal to 0, we have no linear correlation. But you might find another type of relation between them. These are the examples that we saw. Perfect positive correlation, strong positive correlation. Now, please pay attention to these numbers. 100%, 81%. Weak positive correlation, 45%. Negative 100% or -1, which is perfect negative correlation. Negative 0.92, negative 92%. You have a strong negative correlation. And here we don't have any linear correlation. Basically have no linear relation between X and Y. So for example, if you pass in 90%, the visualization is going to be similar to this. You can easily recognize a linear trend, strong linear trend between X and Y. Well, if we see a graph like this, it means that you have a weak correlation. So this can be associated to 25%. Still, we see a positive trend, but it's difficult to recognize the pattern. If you pass in 0, we expect to see no recognizable pattern in the linear form. And if you pass in negative 0.55, we expect to see a weak negative correlation, which behaves like this. Decreasing trend. Let us calculate R. Import pandas as PD, matplotlib.pyplot as PLT, and Seaborn as SNS. We're going to read our table, the hybrid models, and we're going to define a for loop. Let me share the code with you so you can run this in your Jupyter notebook. These are the rest of the codes. Please make sure to run them in your Jupyter notebook or Google Colab, whichever IDEs you're using. There we go. Okay, it's a long code. Just give me a moment. And we're setting up the grid. This is the rest of the code for you guys. Take your time. Type them in your Jupyter notebook. Run the code. We're going to see an amazing sets of scatter plots with their correlation coefficient, showing any linear relationship between them. The breakdown of the code, as you remember, we're going to use pandas for data manipulation, matplotlib.pyplot to have a good visualization, and then we're using Seaborn, which is built on top of matplotlib and provides more attractive and easy to use plotting functions. We are using .corr, which is basically the correlation coefficient method. To find a correlation coefficient for us. SNS.set. It basically set the style of the seaborne plots. And then we have our loop. This loop basically iterates over all pairs of columns in the correlation coefficient matrix I and J. We have two columns, column 1 and column 2. Taking I from column 1 and taking J from the second column. If you have the data set on the main diagonal, it means that I and J are equal to each other. It basically displays the variable name or your column 1. Why is that? Because you want to avoid plotting redundant scatter plots. And for the ones else that are not on the main diagonal, it basically generates the scatter plot for you. Take your time, run this line of code. You should see a very nice scatter plot set with their correlation coefficients next to them. You have about 21%, 36%, negative 17%. So this guy that shows year, it is year and year. This guy shows MSRP, it's MSRP and MSRP. Here you have acceleration and acceleration. That's why you see the repeated names. It's just to avoid redundant scatter plots. The correlation coefficients are next to the scatter plot. And negative 53% shows that, hey, we almost see a decreasing trend, even though it's more like a curve than a line. For example, here you have a lot of noise, right? So it calculates the correlation coefficient to be 36%. These are not good correlation coefficients. These are showing we have very weak correlation between linear correlation between X and Y. We can also use the heat map. And let me show you here. This is a heat map correlation matrix that shows the correlation coefficient between each two variables. 100%, 100%. So we expect two variables have the perfect correlation if the variables are the same year and year. MSRP and MSRP, acceleration and acceleration, MPG and MPG. For example, for year and MPG, you have a negative correlation. And it's very, very weak. Negative 17%. This is not good. So between MSRP and acceleration, you have 70%, which shows a good, not very strong, but good correlation. The rest of them are mainly weak, like negative 51%, negative 53%. Let's go back to the slides and let me share the codes with you so you can run this. Take a few moments, run this line of code. These are interesting pieces of information in analyzing your model, finding relation between X and Y. There's a common interview question that they're asking you to visualize all of the scatter plots. Sometimes they ask you to have the correlation coefficients next to the graphs as well. So it's a very good way to visualize them. And if they ask for the heat map, I just showed you how to create a heat map using SNS.heatmap. So instead of using data science library, we're using more standard library in Python, like NumPy, like SNS. If the interviewer is not familiar with data science library, you have to go to other measures and explain the steps. But remember that data science library is mainly for educational purposes. Very good. We're ready to talk about regression line. Remember that the correlation coefficient R doesn't just measure how clustered the points in a scatter plot are about a straight line. It also helps identify the straight line about which the points are clustered. In this section, we will retrace the path that Galton and Pearson took to discover that line. As we have seen, our data set on the heights of parents and their adult children indicates a linear association between the two variables. The linearity was confirmed when our predictions of the children's heights based on the mid-parent heights roughly followed a straight line. Let us take a look at our table. Let me share the code with you. Make sure to import your useful library. We are on family heights. Make sure to load your CSV file. As you saw before, we're basically creating a new table with mid-parent column and the child's. And as you remember, we defined a function that returned a prediction of the height of the child. And remember, we defined close points. Those are the points that the mid-parent are in between the height minus 0.5 inches and the height plus 0.5 inches. It's going to return the close points which basically extracts the column child from the filtered row, which is basically your close points, and compute the mean or average child height for these rows. Now let us take a look at the heights with predictions scatter plot. This is what we see. So basically, you can see a good line, an increasing line. So it suggests that we have a linear relation between x and y. But how do we measure in standard units? Remember that our goal is to be able to visualize this in a standard visualization. Let's see if we can find a way to identify this line. First, notice that linear association doesn't depend on the units of measurement. we might as well measure both variables in standard units. So let us define a function. The function is called standard underscore units. You pass in x, y, z, and it converts any array of numbers to standard units by finding the difference between that array of numbers and the mean and divided by the standard deviation. Let us take a look at two columns, including a mid-parent in standard unit and a child in standard unit. Okay, you see the difference. Some of them are negative as well, below the center, and so on. Some of them are above the center, some of them are close to the center. A breakdown of the line of the code. We're basically using NumPy mean and NumPy standard deviation to standardize these values. On this scale, we can calculate our predictions exactly as before. But first, we have to figure out how to convert our old definition of close. Again, we are going back to the topic of near or neighborhood. Close points to a value on the new scale. We had said that mid-parent heights were close if they were within 0.5 inches of each other. Since standard units measure distances in units of standard deviations, remember we talked about this before, we have to figure out how many standard deviations of mid-parent heights correspond to 0.5 inches. So let us begin. One standard deviation of mid-parent heights is about 1.8 inches. So 0.5 inches is about 0.28 standard deviations. Let us calculate the standard deviation of the heights. The standard deviation is 1.80. So we're using numpy.std, which is numpy standard deviation of mid-parent column. And when you pass in 0 for the column, it basically extracts the first column. But what's the meaning of 1.80 as the standard deviation? If we were to calculate this 5 inches and divide it by the standard deviation of mid-parents, this value is going to be 0.28. So in standard unit, you have 0.28. This divides 0.5 inches by the standard deviation of mid-parent heights, which tells us how many standard deviations 0.5 represents. Remember that our standard deviation is 1.8. So if you do the division, 0.5 by 1.8, this is 0.28. So it means that 0.5 is approximately 0.28 standard deviations in a standard unit. We're now ready to modify our prediction function to make predictions on the standard unit scale. All that has changed is that we are using the table of values in standard units and defining close as above. So let us define our function. The function predict childs in standard unit. It returns a prediction of the height in standard units of a child whose parents have a mid-parent height of mid-parent height underscore in standard unit in standard units. So what's the scatter plot look like? A scatter plot for mid-parent in standard unit and child in standard unit, the behavior is exactly the same as we saw before, but the scaling is a little bit different. Now you have 0, 1 unit to the right, 1 unit to the left, 2 unit to the right, 2 unit to the left, and so on. But the behavior of the scatter plot is the same. This plot looks exactly like the plot drawn on the original scale, only the numbers on the axis have changed. This basically confirms that we can understand the prediction process by just working in standard units. So let me share the code with you. This was our parent average. You get the exact same result. Very good. So let's go back to our slides. And now for the regression line itself. The regression line in the units of the data. The correlation between the mid-parent height and the child's height is 0.32. We can calculate the correlation. Either use the correlation function that you define, or you can use the correlation function in the library. Either is fine. Both should give you approximately close values. 0.32. This is the correlation coefficient between these two variables, x and y. This is not a good correlation coefficient. It shows we have a weak correlation. We can also find the equation of the regression line for predicting the child's height based on mid-parent height. To do that, as you saw before, we need the slope of the line. We need the intercept of the line as well. Slope of the line is about 60.64, and the y-intercept is about 22.64. We're using slope and intercept functions. The equation of the regression line, as you remember, is y hat equals to mx plus b. We have our slope and we have our y-intercept. Just calculated these using the slope and intercept functions. Now we can make predictions as well. We can plug in different values for our mid-parent height and do the prediction for estimation of child's height. As you remember, this is also known as the regression equation. We are using regression equation which help us to predict y value using x. For example, for a mid-parent height of 70.48 inches, the regression equation predicts the child's height to be 67.56 inches. Multiply the slope by this new x plus the y-intercept, and it generates the predicted y value of about 67.56 inches. So you can now easily find the deviation between the y and predicted y value. You can also find the average y values and do the explained deviation and unexplained deviation as well. Our original prediction, created by taking the average height of all children who had mid-parent heights close to 70.48, came out to be pretty close to 67.63 inches, compared to the regression line's prediction of 67.55. So in a sense, we're basically working with explained variation, unexplained variation, total variation that we explained at the beginning. Now, just take a look at the mid-parent, where the height is equal to 70.48, and we just look at the three of them. The mid-parent height is 70.48. This is what we said. The child's height is 74, and the prediction is way off. So this is the child's height, the actual child's height. This is the predicted value, which is 67.63. Child's height is 70, and the predicted value is 67.63. Well, okay, are we doing a good job using this as a regression line? Probably not. So again, our goal is to minimize the sum of residuals squared. Here are all of the rows of the table along with our original predictions and the new regression predictions of the children's heights. In that case, what do we have? We have basically, please note that some of them are just presented here and the rest are just omitted. You have the mid-parent, you have the child, you have the prediction, and you have regression prediction. So comparing the child with the regression prediction. 73.2, 70.7, 69.2, 70.7, 69, 70.7, 69, 70.7, 73.5, and 69.58, and so on. Take a look at the scatter plot. The prediction line and regression line are very similar. So it means that hopefully we did a good job, even though our correlation coefficient was 32%. So we might either need more data or we need other mathematical model to analyze the relation between X and Y, because the correlation coefficient was just 32%. On the method of least squares, remember that we've developed the equation of the regression line that runs through a football-shaped scatter plot. But not all scatter plots are football-shaped, not even linear ones. Does every scatter plot have a best line that goes through it? This is a general question. If so, can we still use the formulas for the slope and intercept developed in the previous section? Or do we need new ones? To address these questions, we need a reasonable definition of best. Recall that the purpose of the line is to make prediction or estimation. And when you're talking about prediction or estimation, you always end up with an error. Estimates typically aren't perfect. Each one is off the true value by an error or a residual. A reasonable criterion for a line to be the best is for it to have the smallest possible overall error among all straight lines. In this section, we'll make this criteria precise and see if we can identify the best straight line under the criteria. Our first example is a data set that has one row for every chapter of the novel Little Women. The goal is to estimate the number of characters, that is letters, spaces, punctuation marks, and so on, based on the number of periods. So let's take a look at our table. Let me share the line of the code with you. So you can take a look at the table, analyze this, make sure to import the important libraries that are going to use, and we want to use a scatter plot to visualize the relationship. Then make a decision. So for example, the first column has the number of periods and the second column has the number of characters. 189 periods and you have 21,759 characters. The number of periods is 188. The number of characters is 2248 and so on. But do we see any relationship between X and Y's? And if there is a relationship, is this a linear relationship? So this is the type of question that we're interested in answering. Let us take a look at our scatter plot as usual. Visualization is the very, very basic step in analyzing the data. The number of periods and the number of characters. So from visualization standpoint, we're basically seeing a linear relation between X and Y. And it seems like we have a positive trend. To explore the data, we need to use the functions correlation, slope, and intercept and fit. Let us find the correlation coefficient between periods and the number of characters. Very good, very impressive. Seems like we have a strong correlation between these two variables. Let me share the line of code with you so you can run this in your Jupyter notebook. This is the standard unit and the correlation function and the definition of slope and the intercept and the fit. So as you can see, the correlation between periods and characters is 92.30%, which is suggesting a positive correlation between these two variables. It means that as the number of periods increases, the number of characters also tend to increase in a fairly linear way. Now let us discuss the error in estimation. Let's take a look at the scatter plot and basically have the line of prediction. Little Women with prediction. This is a copy of the original Little Women containing the data on the number of periods and the characters. We're looking at the scatter plot for the periods and the characters, and basically we have the linear prediction. Is this the same as the regression line? How close they are? What if I change these? What if I change the slope? What if I change the y-intercept? So these are the types of questions that we try to answer and basically get the result of, get the conclusion that the least square line or the regression line is the best line for prediction. But again, as long as you have a linear relation between x and y, you're allowed to do that. If it's non-linear, well, it means that we have to switch to different models. Corresponding to each point on the scatter plot, there is an error of prediction. We can calculate the error of prediction as the actual value minus the predicted value. It's the vertical distance between the point and the line with a negative sign if the point is below the line, as we visualized at the beginning of the lesson. So for the Little Women with predictions, we're focusing on the characters column. We set it as the actual value. The predicted value, we're using the Little Women with predictions column when we use the linear prediction. And the error or the residual is the difference between the actual value and the predicted value. But what's the visualization look like? Let us take a look at some of the errors. The difference between the actual value and the predicted value. For example, the number of characters minus the number of predicted values. It's 575.403. Some of them are positive, some of them are negative. So these are the collection of errors, and some of them are not written here. We can use slope and intercept function to calculate the slope and intercept of the fitted line. The graph below shows the line, the errors corresponding to 4 of the points are shown in red. Not all of the errors, some of them. But just for better understanding the behavior of the residuals, everybody. They were just chosen for clarity of display. The function Little Women underscore errors takes a slope and an intercept as its arguments and draws the figure. So we calculate slope, intercept, and then we define the function Little Women errors and calculate the predicted values based on the slope and the intercept. The predicted value, as remember, is slope times x plus the intercept, and the actual values are the values that are located in the column, the character. So it happens that the slope of the regression line is 87 with y-intercept to be 4,745 characters. Okay. We can also take a look at the regression line, or in this case, the predicted line, with some of the residuals. Some of them, again, there's nothing special about these lines, just for the sake of understanding the behavior of the residuals. So as long as the actual value is below the regression line, the residual is negative. If the point is above the regression line, the residual is positive. And if those points are exactly on the line, we have 0 residuals. Remember that our goal is to minimize the summation of residuals squared. This is what we want. Had we used a different line to create our estimates, the errors would have been different. The graph below shows how big the errors would be if we were to use another line for estimation. The second graph shows large errors obtained by using a line that is downright silly. So let's take a look at the 50 slope and 10,000 y-intercept. The errors behave like this. As you can see, now you have a larger red line, which is showing the error or residual between the actual value and predicted value. What if we pass in other slope and y-intercept? Suppose I pass in a negative slope, like negative 100 and y-intercept of 50,000. What's the graph look like? We have more residuals, and they are longer in size. Now we're going to use root mean squared error. What do we need now is one overall measure of the rough size of the errors. You'll recognize the approach to creating this is exactly the same way as we developed the standard deviation. If you use any arbitrary line to calculate your estimates, then some of your errors are likely to be positive and some of them are probably negative. As you remember, to avoid cancellation when measuring the rough size of the errors, we'll take the mean of the squared errors rather than the mean of the errors themselves. The mean squared error of estimation is a measure of roughly how big the squared errors are. But as we have noted earlier, its units are hard to interpret. We're going to take the square root, so we get the exact same unit as the variables. Perfect. Minimizing the root mean squared error. Remember that RMSE or root mean squared error might have different names in different books. Sometimes it's referred to by other names or compared to closely related metrics, including root mean squared deviation, RMSD. This term is often used with root mean squared error, especially in physics, chemistry, and engineering. You might also hear standard error of estimate that we introduced in statistics. In linear regression, root mean squared error can be considered the standard root of estimate, which indicates how well the regression line fits the data. You might hear quadratic mean. Although less commonly used, quadratic mean describes the concept of taking the square root of the average of squared errors, or L2 norm of residuals. In optimization and regression, the root mean squared error is often associated with L2 norm because it minimizes the sum of squared residuals, aligning with the principle of least squares. Our observations so far we summarized as follows. To get estimates of y based on x, You can use any line you want. Every line has a root mean squared error of estimate. Better lines have smaller errors. So basically we get smaller root mean squared error. But is there a best line? What is that line? How we can define the best regression line? This is basically the line that has the minimum root mean squared error. To answer this question, we'll start by defining a function, little women, RMSE, representing the root mean squared error to compute the root mean squared error of any line through the little women scatter diagram. This function takes the slope and the intercept as its argument. So let me share the code with you. So you can run this in your Jupyter notebook. Please run these line of codes in your Jupyter notebook or Google Colab. So let us define this function that takes two arguments, slope and the intercept. And it basically fits that into the model. So if we calculate the root mean squared error when slope is 50 and the y-intercept is 10,000, the root mean squared is 4,322. And the visualization here is as follows. You have some of the residuals represented here. We can pass in more slope and y-intercepts. So now what if I pass in a negative slope with 50,000 as the y-intercept? In that case, the root mean squared error is 16,710. Wow, it increased to a very large number. So now if you use a line with negative slope, as you can visualize, these are your residuals. Remember that bad lines have big values of root mean squared error as expected. But the root mean squared error is much smaller if we choose a slope and the intercept that is close to the regression line. Won't believe me? Take a look. If I pass in 90 and 4,000, I get the root mean squared error to be 2,715. So remember that when it comes to machine learning and you're getting these numbers, you're looking at these values, even though the root mean squared error looks large, you're comparing these values with the actual values in your data. They might look like big numbers, but again, comparing to the values that you have in your data set, they might be negligible. So that's very important to always take a look at your data. What is the type of data that you're looking at? For example, here you have the number of characters, you have 10,000, 15,000, 20,000, and so on. So a 2,715 looks very okay. Here is the root mean squared error corresponding to the regression line. By a remarkable fact of mathematics, no other line can beat this one. The regression line is the unique straight line that minimizes the mean squared error of estimation. So if we pass in slope and the y-intercept into our function, it generates the root mean squared error of 2701.69. Here we have the regression line. Some of the residuals are located here. And as you can see, the residuals are well behaved. The proof of this is basically related to math proof, which is beyond the scope of this course. Numerical optimization. First of all, note that a line that minimizes the root mean squared error is also a line that minimizes the squared error. The square error makes no difference to the minimization. So we still save ourselves step of computation and just minimize the mean squared error. We're trying to predict the number of characters y based on the number of periods x in characters of the little women. Well, if we use the line y hat equals to mx plus b or ax plus b, we'll have an MSE which is mean squared error that depends on the slope m or a and the intercept b. The function little women of mean squared error takes the slope and the intercept, and its argument are these two values, slope and the intercept. And it basically returns the corresponding mean squared error. Let us pass in some values for this function and see what do we get. You can also compare this with the root mean squared error of the regression line. Remember that the little women mean squared error returns the mean squared error, so we have to take the square root to get the root mean squared error. That's the main difference between these two. So if we just look at the mean squared error of the slope and the intercept, and then take the square root of it to define the root mean squared, this is basically 2701.69, which is the same as what we saw before. That's the same as the value we got by using the root mean squared error earlier. If we take a look at this one more time, we can see that the root mean squared error is 2701.69. And this was our regression line. You can also confirm that for the little women, mean squared error returns the correct value for other slopes and intercepts too. For example, here's the root mean squared error of extremely bad line that we tried earlier. If you pass in negative 100 and 5,000 and take the square root of it, then it generates 16,710, which is a very, very large number. If we experiment with different values, we can find a low error slope and intercept through trial and error. But that would take a while. Fortunately, there's a Python function that does all the trial and error for us. The minimize function can be used to find the arguments of a function for which the function returns its minimum value. Python uses a similar trial and error approach, following the changes that lead to incrementally lower output values. The argument of minimize is a function that itself takes numerical arguments and returns a numerical value. For example, the function little women mean squared error takes a numerical slope and a numerical intercept as its arguments and returns the corresponding MSE. The call minimize of little women mean square error returns an array consisting of the slope and the intercept that minimize the MSE or mean square error. These minimizing values are excellent approximations arrived at by intelligent trial and error, not exact values based on formulas. For example, if we just take a look at minimizing the little women mean squared error, it generates the following array for you. These values are the same as the values we calculated earlier by using the slope and the intercept. We see small deviations due to inexact nature of minimize, but the values are essentially the same. If we compare this with the actual slope and the y-intercept, we can see that the slope from the formula is 87.98 and slope for minimize is 86.98. Very close. So you have just some different values for on the right side of the decimals, but mainly these numbers are very similar. Therefore, we have found not only that the regression line minimizes mean squared error, but also the minimizing mean squared error gives us the regression line. The regression line is the only line that minimizes mean squared error. That's why the regression line is sometimes also called the least square lines.